All right, again, welcome. This is Thursday, March 7th, 12 to 1, Math 123, Section 03D. And just a reminder about things that are due. We have Web Work 8 and the Excel trend lines and discussion board number 4, all due tomorrow, March 8th. And then today's work is in the exponential models and interest, and Web Work 9, Excel models, and quiz number 4 are due on March 22nd. So we do not have class next week, which would have been March 14th. We don't have class next week due to spring break. And so the assignments that would normally be due next week are due the following week, March 22nd. So that's where we are. We do have an exam coming up, our second exam. It covers, looks like sections 7 through 12. And that is going to be the week of April 1st. So around that week, April 1st. Let me look at my calendar here. April, so yeah, so March 31st, April 1st. So that's the week that we're going to be doing our review, April 4th. And then the exam will be due, either do it that week after our review, preferably, or the following week, due on April 13th, okay? So that's when the exam is coming up. So make sure you go ahead and schedule that so there's no conflicts. And let's get started on page 107. So we're looking at exponential modeling today. Exponential growth, and it says here, consider the following situation. Oliver opens a retirement account by depositing $1,800 in the initial year. He intends to increase his deposits by $100 in each subsequent year. So it asks here, how much does Oliver expect to deposit in year 1? So let's just make a note. In year 0, that's his $1,800 deposit. So in year 1, if he's going to increase that by $100, how much is he going to deposit in year 1? Yes, don't struggle with that one, $1,900. And how about year 2? Year 2, $2,000, that's right. So let's finish this up here, $2,100 if I'm filling out the table, and $2,200. So what this table asks us to do is find the absolute and relative change. So remember, the absolute changes, you just subtract these two consecutive values, 1,900 minus 1,800. So I'll do the first calculation here, 1,800. That gives us $100. And then subtracting these two, you guessed it, $100. So each year, the absolute change is $100 because they're increasing it by $100. Now the relative change is a little bit different. The relative change is taking that increase, 100, and dividing it by the previous year's amount, or the previous year's deposit. So 100 over 1,800 is going to be the first one. And we'll just write the relative change here as a decimal. Let's see, dividing those, I get 0.056. Yes, thank you, Caitlin. And so, oops, almost, Caitlin, it's 0.056. And so the percent then is move the decimal 2 places to the right, and it becomes 5.6%. Okay, and then let's see, the next one is going to be 100, the absolute change, divided by the previous deposit, 1,900. You can see we're dividing by a larger number, so our relative change is going to go down a tiny bit. In this case, it's 0.053. There we go. So 5.3%. And then the next one, 100 divided by 2,000. That is 0.05. So 5%. And then 100 divided by 2,100 is 0.04, let's say 8. So 4.8%. So this asks us a pretty straightforward question here. How is the total amount of deposits changing from year to year? And we've already mentioned this. We're just adding $100 each year. And then it says, which value stays the same, the absolute change or the relative change? Brian's got fast fingers today. Awesome. The absolute change is staying the same, right? You can see that it's all 100 right here, right? They're all 100s. It's all staying the same. It says next, without continuing the table, how can you mathematically find the total amount of Oliver's retirement contributions in the 6th year? So without continuing the table, how can we find it for the 6th year? Well, we can take $100 times 6 years and then add that starting amount to it. And if you do that, you get $2,400. And that should make sense because year 5 is going to be $2,300 and then year 6 is $2,400. So it says use the initial value for year 0, the absolute change from year to year, and the pattern by which the value of the deposits are increasing to find a mathematical model that will give the amount of the deposit in any given year. So this is almost the model right here. Remember, the model has a y and an x in there, 2 variables. We'd say y equals m, the slope. So the slope is the rate of change. It's changing by $100 every year. And then x would represent the number of years. And then remember that the starting amount is the y-intercept. So this would be the mathematical model, where x is the number of years since the initial year. And then it asks, what kind of model is this? Perfect, Megan, it is a linear model. And Nicole. So it's a linear model. So what you need to note is this piece right here. When the absolute change remains the same from period to period, we have a linear model. And the absolute change is the slope. Slope is the absolute change. And the y-intercept is the starting amount. Okay, so that's exactly what we did. There's the slope, the absolute change, and here's the starting amount. Flipping the page here, it says, let's try another strategy. What if Oliver increases his deposits by a percentage each year rather than a specific dollar amount? So from our previous scenario, Oliver realizes that $100 is roughly 6% of his current contribution. He decides to increase his deposit by 6% in the coming year, then increase that by 6% in the following year, and so on. So number 8 asks, if Oliver increases his total retirement deposits by 6% in the first year, how much money will be deposited by the end of the first year? So again, remember, he's starting with that $1,800. And how do we show a 6% increase? Remember that formula we had before that said new equals 1 plus the percent increase times the old. So 100 plus 6% is going to be 1.06. That's right. So we're taking the new amount is going to be 1,800 times 1.06. So that'll get us the next value. Let's see, 1,800 times 1.06. That is 1908, yes. So here's what we have. We have 1,800 times 1.06 is 1908. Now to get the next year, we're going to take 1908 times 1.06. And it is 2022 and 48 cents. And then we're going to take that answer times 1.06. And again for the last one. All right. So now we can see that the absolute change is different every time. So in the first one, we have 1908 minus 1800, and that is, what is that, $108? And then I'm just going to subtract these for you and write the answers in just to save us a little bit of time because we have so much to do today. 114.48, and then 121, if I subtract these two, 121.35, and the last two, subtracting those, we get 128 and 63 cents. So those are the absolute changes. And then let's find the relative change. So this time, we're still going to take the absolute change divided by the previous value. So 108 divided by 1800. And it is 0.06. So when we take the next one, 114.48, we divide that by 1908. And we get the same result, 0.06. And that's what we'll get for each of these, as a matter of fact, which is 6%. Oh my goodness, imagine that. Oliver is increasing his deposits 6% each year, and our relative change is 6%. So now we don't have a linear model anymore because these values are different every time. We don't have a linear model. So question 10 says, how are the total of deposits changing from year to year, and what is the mathematical rule to find the next year's total of deposits? And so we know that the deposits are increasing by 6%, and what the rule was multiply by 1.06 each year. So it asks which value stays the same. And this time it's the relative change. All right, I'm going to take just a brief second here and update my attendance. Make sure I have everybody here. All right, perfect. So it says, without continuing the table, how can you mathematically find the amount of the total of the deposits in the sixth year? Well, we can do 1.06, we'll do 1800 times 1.06, so we could just put that 1.06 in there 6 times, right? And there's a much better way to write this. 1, 2, 3, there's 4 of them, 5 of them, 6 of them. Whoa, so a better way to write that is what Caitlin noted for us. Let's see. So it's 1800, the starting amount, times 1.06, and an exponent tells us how many times to multiply something by itself. So in this case, we're multiplying the 1.06 by itself 6 times, and so we can use the exponent of a 6. Yeah. Perfect. And so I see a couple of you have that in the chat box. So 1800 times 1.06 to the 6th power gives us for the 6th year 25, 53, and 33 cents. Now this model is not a linear model. It's called an exponential model. And in this case, it's exponential growth because the relative change is positive. So it says, here's a formula. The amount equals the initial amount times the growth factor to the time period power. And I don't like this saying percent there. It's really the relative change. So the growth factor is 1 plus the relative change. So 1 plus 0.06 is 1.06. That's the growth factor. That's the number that goes right here, as you noticed. So that answer is actually that one. And it says the growth factor can also be found by taking two consecutive data points from the table and dividing them. So let's take 2 points and divide them. So I'm going to take, let's see, I'm going to take year 3 and year 2. So year 3 is 2143.83, and year 2 is 2022.48. And if we divide these, we should get 1.06. We do. So 2 different ways to find the growth factor. We can do 1 plus the relative change, or we can take 2 consecutive values and divide them, the newer one divided by the older one. So we've already talked about that. So it says here, here's a graphic comparison of linear and exponential models. So the blue dots, those are the linear models, adding $100 every year, and the reddish diamonds are the exponential model, which is adding 6% every year, or multiplying by 1.06. And it says, notice the difference in retirement contributions with each passing, it increases with each passing year. So this isn't the amount in the retirement account, this is the amount of the contributions. Okay, so that means that in year 30, Oliver would be contributing about $4,500 if he was doing the linear model, the increasing by $100 every year. And in year 30, he'd be at about $10,000 to deposit that year. And so this first number 15 says estimate the difference between the contributions at 35 years. So 35 years, this looks like about 14,000 minus this one here. I don't know, probably close to 4,800. I don't remember. We're not going to necessarily have to calculate that, but just pitch it on there. Or wait, 5,550. Let me try that again. Maybe 55 or 5,800. Yeah, 5,800. Sorry about that. So maybe approximately $8,200 difference. So after 35 years, Oliver would be depositing $8,400, $8,500, somewhere in there, more by increasing his deposit 6% each year rather than increasing them by $100 every year. So that shows the difference in the two growth. So linear growth, straight line, exponential growth, it's a curved line. It could be curving upwards or downwards. It just depends if it's growing or decaying. So let's look at page 110 and do some calculations here with this growth factor, exponential growth. So it says here, according to the United Nations, in the year 2000, the world population was approximately 6.2 billion. Assuming the population has grown by 1% per year, answer the following questions. What is the growth factor? So if it's growing by 1% per year, what would the growth factor be? Thank you, Megan. 1.01, right? 100 plus 1% is 101%, so 1.01. And Stephanie, so it says, what is the unit of time? What is the time being measured in here? Years. And then it says, what is the exponential equation for the world population using the population in 2000 as a starting point. So we'd say the amount, or we could put a y there. The amount is, now we're going to put the starting amount in, 6.2. And I'm not going to put the billion in. We'll just know that at the end, our answer is going to be in billions. And we put a parentheses to signify multiplication. And then we're going to throw the growth factor in, 1.01. And then the power is going to be the t power, the time power. And just note that t is years since our starting year, 2000. And then this next question asks us to use this to estimate the population in 2014. So let's do that. Now, when we do this, I want to make sure that you can do this on your calculator. You're either going to use the caret button, so the caret, and then the number of years, or there might be a y to the x button on your calculator. You could use that one also. So we would type in, so we'd have y equals, we're not going to type that in the calculator, but the next part, 6.2, 1.01, and then you can use the caret button in your calculator, and then the number of years, which is 14. Thanks, Caitlin. And then make sure that you can put that in your calculator correctly, because if you can't, we want to resolve that right now. And you should get 7.13-ish. Yep. And then note that, remember that this initial value was in billions, so we need to put this as billions. So take a moment, make sure you can do that in your calculator. Okay, so are there any questions so far? Questions so far? All right, looking good then. So let's move to the next half. Oops, let's see. There we go. So flipping over to page 111, we're going to talk about exponential decay. And again, so it's really the same idea. It's the decay factor is 1 minus the percent change, but it's really still 1 plus the relative change. Now remember that sometimes the relative change is positive and sometimes it's negative. So if the relative change is negative 0.05, then 1 plus that is really 1 minus 0.05. Okay, so that's one way we can calculate it. Again, using 2 consecutive data points will also get it for us. Formula is the same. The initial amount, decay factor, time period. So let's look at these examples here. Number 1 says, and this is on the bottom of page 111, it says airline miles have a tendency to lose value over time as airline companies change or update policies. Alicia traveled often for business and had earned 500,000 frequent flyer miles prior to her retirement. She estimates that her miles lose around 26% of their value from year to year. She wants to know what the decay factor is. So if we're going to do this in percents, it's really 100% minus 26%, since she's losing 26%. So what percent is that? 74%. Now we don't want the percentage, we want the decimal, so the decay factor is going to be 0.74. We also could have done this by taking 1 minus that 26% as a decimal. What is the unit of time? Yep, it's years again. And then it says construct an exponential model to approximate the value of her airline miles for any given year. So the amount is the beginning amount, 500,000. Sorry about all that sloppiness with my mouse that I'm writing with. Then the decay factor, 0.74 to the t power, and then note that t is number of years since retirement. Since it says she has 500,000 when she retires. And then asks how many will remain after 5 years. Let's see. The amount, 500,000, 0.74 to the 5th power. And it is 110,950 miles. Make sure you don't put a dollar sign in there, right? Okay, so let me look here. This doesn't take into the fact airlines. Well, they do. They do. All right. Page 112. Is comparing antibiotics, and it shows, the decay rate. Basically, they're losing a certain percentage of their effectiveness every hour, and it really is an explanation of why different drugs you have to take another dose after a certain number of hours. Okay, but I think you have an assignment on dosage calculations in that. So page 113, it says using exponential models, you should be able to determine the exponential model and find future value when you are given the initial value and either change or the growth or decay factor. And so let's try it. Uh-oh. All right. How is this? Can you hear me okay at this point? All right. It's just I turned to look at my book, and somehow when I turn, it just doesn't give the same boom effect as it normally does when I'm facing my screen here. So, all right. So it says use the graph to answer the following questions. How is the number of life forms changing from day to day? And we want to be specific about this. So we look at this graph and it says new life form. Number of life forms is along the side and days since discovery is along the bottom. So from one day to the next, what's happening to the life forms? The number of life forms. Yeah, so not only is it increasing, but it's actually doubling, like it was mentioned. So it went from 40 to 80, then 80 to 160, then 160 to 320, 320 to 640. So it's actually doubling. Not only is it increasing, but it's doubling. If something is doubling, what are you multiplying it by? Just as a side note, you're multiplying it by 2. So remember when we were multiplying by 1.06, that was the growth factor. So if we're multiplying by 2 for doubling, that's going to be the growth factor. What if it was tripling? Then what would we be multiplying by? We'd be multiplying by 3. That's right. So just because we don't have the numbers given doesn't mean we can't find the growth rate or the decay rate. So here it says, what is the initial value? That's the starting amount. And that is 40. The starting amount is right here at time 0. What is the unit of measure? Well, it looks like days this time. And then we're going to construct the model. And actually, instead of writing amount, I'm going to write y equals. We have the starting amount times the growth factor, which we know is 2 to the t power, or the x power if you want to use x. And then again, t is the number of days since day 0. So letter E says, use guess and check to determine when the number of life forms will reach 2000. So this question is a little bit different. This wants us to find the time, not put the time in. So this really looks like this. 2000 equals 40 times 2 to what power? And we're trying to find out how many days it's going to take for these to reach 2000. We can look at this and go, okay, it took 4 days to get to 640. And if we double that, that's going to be 1280. So that's day 5. And then 2560, if I double it again, that's going to be day 6. So it's going to take more than 5. So let's say 6 days. So that's using guess and check. Another way we could do this is we could just put a number in for the t. You could just try some values for t. And if you put in 5, you'd see that you get 1280 out. And that's not enough days. If you try 6, you can see that that's more than 2000, so that is enough days. So you could either try it by putting values in for t in your calculator, or just going through the process here of doubling from wherever your data ends. Let's look at the other question on that page, on the bottom of page 113. It says high definition TVs are averaging $1,500 currently, but costs are decreasing at a rate of 15% per year. And then I want you to take a few minutes. I'm going to give you, let's say, 3 minutes and answer these 3 questions, okay? Now don't put your answers in the chat box, just put a hand raise when you've got those 3 questions answered. All right, so I know it's been 3 minutes. That was a fast 3 minutes. And a few of you are done, so let's take a look and see where you are. Is this a case of exponential growth or is it a case of exponential decay? I think we've got a couple answers in there already. It's decreasing, so it is exponential decay. And construct a model. So here we have y equals, or amount equals, the beginning amount, $1,500. And then the decay factor is going to be 100 minus 15. So as a decimal, 0.85. To the t power. Yep, just like you guys have in there. Well, Caitlin, make sure you have that little caret before your t. All right. And then if you're just writing it, make sure the t is a little tiny t up above as an exponent. So now we're asked to find how many years will it take for them to reach half of their original cost. And so you just have to put some numbers in till the value gets below 1,500. Or you can do 1,500 times 0.85, get that value. So let's find out here. Or you can just test some values, put some values in for t until you get the first one that reaches below $750. So let's see, 1,500 times 0.85 is 1275, so that's not quite there. Whoops, 75 times 0.85 is 1083.75, so that's not there. That's 2 years times 0.85. So the third year is 921.19. So the fourth year is 783. We're almost there. And then the fifth year we get 665.56. So 4 years, it doesn't quite get there. Year 5, it makes it. So 5 years. And again, you can do that using all this work along the side, or you can just test some numbers in for the t until you get the first one that meets the requirement, which in this case would be $750 or below. All right, so the next topic we have is called interest, and there's a couple different types of interest we're going to look at. Limited time that's remaining. And I do want to, let's see, make sure you bring your attention to page 117 and 118, because that is the instructions. Those pages are the instructions for creating a graph like I showed you earlier with the linear and the exponential model both on it. So on page 119, it asks us to take a look at interest. So the first thing we have is simple interest, and the interest amount is called the principal times the rate times the time. Now the balance isn't given to us here as a formula, but the balance is the principal times 1 plus the rate times the time. That's one formula for it. Or another formula could be the balance is the principal plus the PRT, the interest. So it's the principal plus the interest, principal rate times time. Now the rate here in this case has to be, it's as a decimal, okay? So if the rate is 5%, you need to put it as a decimal, 0.05. So this is how you find the balance. This is how you find the interest. So let's see, it says if money were invested at simple interest, then each year you would earn interest only on the original amount that you invested. So if you invest $1,000 and you're earning 4% per year, you're going to get 4% interest on the original amount each year. So $40 each year is what you'll get. It's just going to be the first year you'll get $40, the second year you'll get $40, the third year you'll get $40 more. And so this one wants to know how much interest will be earned in 3 years. Okay, so in 3 years, if you're earning $40 every year, that would be $120, right? And so the reason is because we have the principal, 1,000, times the rate, 0.04, times the time, 3 years. And that is 120. All right, I was trying to figure out where that was coming from. All right. So it says, what would the ending balance be after 3 years? So now we're going to take the principal, the beginning amount, plus the interest earned after 3 years, and that will be the new balance. So notice with simple interest, we're just getting that $40. We're just adding it each year. And because we're adding the same amount each year, that is a linear model. Okay, remember way back in the beginning of class today, we talked about adding $100 each year, and it was a linear model. So adding $40 every year is a linear model. But generally, simple interest isn't an interest calculation that's used in real life. Most investments use something called compound interest, or most, if you're paying on a credit card, or if you have an interest earning bank account and you're earning interest, it's compounded. It's called compound interest. So it says here on page 120, when money is invested earning compound interest, it earns interest not only on the principal, but also on the accumulated interest of previous periods. This is sometimes it says this is sometimes described as earning interest on interest. For now, we will assume that interest will be calculated once per year. It is important to remember that compound interest savings accounts are based on a single lump sum deposit into an interest-bearing account. So we're just making one deposit and then letting it earn interest over the years. And here's what the formula looks like. So it's an exponential model, and again, remember the rate is as a decimal. So it's the balance is the principal times 1 plus the rate to the time power. So let's look at how this works with the same idea, just compounded annually rather than the 4% simple interest. So in year 1, you would have 1,000 times 1 plus 0.04 to the 1 power, which is $1,040. In year 2, you'd have the 1.04 to the 2nd power, which gives us $1,081.60. Notice that the difference here in interest is $41.60. So the first year was $40. The second year they earned $41.60 in interest because they were getting interest on $1,040 rather than just the original $1,000 like in the simple interest example. So let me fill these in for you. You can check them later. And then the 5th year, 12.16 and 65 cents. So look at year 3. Remember year 3 and the other one was $1,120. This is $4.86 more because you're earning interest on top of the interest in this case. So this one is, if our deposit was $1,000, the accumulated interest is $124.86. Notice how it's just $1,000 minus, it's this value minus 1,000, the deposit. All right, so those are the amounts of accumulated interest. And then again, we can subtract these two to get how much interest was earned for year 3. And it looks like $43.26. Just as a side note, that's what this is, kind of saying, okay, the first year was $40. and then it became $41.60, and now it's $43.26. It's not $40 every year like in the previous example. And so we did this one already. $41.60 for year 2. That's $1.60 more. So how much more is this in the first year in that case? Okay. So now let's look at the more complicated piece and finish this up. So this is over on page 122. So remember that this first formula here is compounded annually. That means one time per year. Now we're going to look at compound interest that's compounded periodically. So different than one time per year. And here's the formula. And this will be on your formula sheet you can use on your exam this time. And the formula sheet should be available at your proctoring center. So let's take a look. Not all compounding is annual. Often compounding is quarterly, monthly, or even daily. The concept is the same, just divide the annual percentage rate by the number of compounding periods and convert the years to the total number of periods. So I don't want you to look at this part right here. Okay, don't look at this. This is not anything that's really concerning us. So it says here, here's the example. $100 is invested for 3 years with an APR that's an annual percentage rate of 11% compounded quarterly. If that's the case, compounding occurs 4 times per year. Okay, quarterly, 4 times. So here's what the formula looks like. 100 times, and all of this stuff is in a parentheses on your calculator. 1 plus 0.11 divided by 4. And then this power has to be in a parentheses also, or you can just write 12 in your calculator if you want to. So let's look at how this works. $2,000 invested at 6%. $2,000, 6%, and we're going to calculate this quarterly. That means 4 times per year. So I'm going to say plus 0.06 divided by 4 for the 4 times per year. Now as my power, my exponent, I have to do 4 times the number of years, because this is how many times you're actually going to earn interest. 4 times a year for 8 years. Or you could put a 32 there if you wanted to. Now let's calculate the balance after these 8 years compounding quarterly at 6%. All right, so in my calculator, I got $3,220.65. Make sure you can do these calculations because you'll have to do them on your exam and in your homework. So compounded monthly, it's going to be the same information, $2,000. Now, this is where the change is going to happen. 0.06 for that 6%. And monthly, how many times per year is that? $12 times per year, right? So we're going to put a 12 down there. And then for our power, we're going to have to do 12 times 8. Make sure that's all in a parentheses on your calculator, or put 96 if you want. So this time, so part A was compounding at 4 times a year. Part B is compounding at 12 times a year. And see what answers you get for that one. $32.28 and 29 cents. Certainly. Now let's look at what happens if we compound it daily. How much would we have? And again, we're using the same information, $2,000, 6% in 8 years. $2,000, 1 plus 0.06. Now this is daily, so how many times a year is that? 365. So now our power is going to have to be 365 times 8. So that's how many times it gets compounded in that 8 years. All right, so how much is that? 32, 3202. And it just wants us to see what pattern there is. So look what's happening. This is 4 times a year, this is 12 times a year, and this is 365 times a year. What's happening to the amount of interest? What's the pattern? The more times you compound, the more interest you earn, right? And that's for a given time period. Mm-hmm. So let me just share with you page 117. So this is the page 117 and 118. It takes you through the steps to put in the linear and exponential models into your graph, into a chart, and shows you how to do that. Okay. So those are the steps, and that's in your book again. And then it's taking this information basically and showing you how to make a graph out of it.